So we got this paradoxical result. We would like to get more clarity about it, and that will come. But to prepare, first some preparatory definitions, concepts will be defined. And I told you this lecture is about situation where two or more components are to be optimized. But now I'm going to talk for a while about situation where only one component is to be optimized. We're just choosing between n tuples, n attribute, maybe commodity bundles, maybe describing how many apples, how many drinks we have, and that is it. So only one component now, not two. Now rows and not matrices we are looking at. And I'm going to repeat a few definitions for that situation. So we have a preference relation over those n tuples, maybe commodity bundles, the usual thing, transitivity, completeness, continuity, monotonicity. Now I'm going to define a condition called separability, and maybe the economists in the audience may remember from the micro class and consumer theory what these things mean, but I'll explain it for everybody so that everybody can understand. I'm going to define now what it means that the first two attributes are separable. Well, assume that we have a preference of this kind. You have two n tuples, but on the attributes 3 up to n are the same. Both of them have Cn standing there, so only in the first two attributes they differ. Now separability says that the preference here is independent of the level where you keep the attribute 3 up to n fixed. So if we replace a C3 3n on the left and the right by D3 dn, preference is not impacted by that. So this implies we have the same preference if we have D's instead of C's. This means in a way that if we think about the preference over the first two attributes, we need not think much about the other attributes. They are not impacting how we choose between the first two attributes. There is no interaction from attribute 3 to n into attributes 1 and 2 going on. So attributes 1 and 2 are separable in that sense. That's what this condition means. You can have, of course, separability not only of attributes 1 and 2, but for every subgroup of attributes you can define separability, meaning the preference over them is independent of the level where you keep the other attributes fixed. Complete separability means that every subgroup of attributes is separable. So then there is no interaction with any pair of groups of attributes going on, total absence of interaction. Weak separability is a very weak condition. Weak separability says only that every single attribute is separable. Let me repeat the definition just so that it's clear. So now we look at the preference between two n tuples. They only differ by the jth attribute. On all the other attributes, they have the same value, cj. And then if we replace those common values by common d values, that does not impact preference. This is separability of the jth attribute. And then weak separability says that every single attribute is separable. Now, one way to see that this is quite weak is that it is implied by monotonicity. For instance, if we have real numbers here, every attribute is a real number, and we say increasing that number, increasing any attribute, increases the n tuple, then that means these two preferences that you see there are equivalent to xj being greater equal yj. So then weak separability is implied by monotonicity. So indeed, it looks like that's a weak condition. Now, behavioral models, they typically operate in what I call the middle ground. I will explain what it means. And in words, it means that usually weak separability, such a weak condition we want to keep, like monotonicity, stochastic dominance, that we want to maintain, but complete separability is given up. Usually behavioral models, they allow all kind of interaction between the attributes going on, and that's why they generalize the classical models, allowing for particular kinds of interactions. Let me give a picture to illustrate the point. Here on the right side, I put the weakest thing that behavioral theories want to maintain, weak separability. On the left, I put the strongest restriction, complete separability. And for instance, if we consider decision making on the risk, expected utility implies complete separability. But the other thing, in fact, stochastic dominance, that is like monotonicity, that already implies weak separability. That can be justified mathematically when I say. Let's skip details now. And then behavioral theorists typically operate in the middle ground. They want to give up the complete separability of expected utility, which is also called sure-thing principle there, by the way. But they want to maintain stochastic dominance. And this happens, for instance, all kinds of theories, non-expected utility, like rank-dependent utility that Quiggin invented, or the new version of prospect theory or disappointment aversion theory. All those kind of theories are in the middle ground. Not only for risk, but for other fields also. For instance, in welfare theory, We want to allow for fairness, that how you feel depends on what your neighbor has. You have interactions of that kind going on, but still improving the income of a person in society in itself has more positive than negative effects always. Sequencing effects can play a role in intertemporal choices. So these are the usual, this is the playground of behavioral theories, you could say. To historically illustrate this point, let me talk about the history of 1979, the first version of prospect theory, a bit different but very similar at the probability transformation theories of Edwards and Honda, for instance. At some stage, end of the 1970s, it was discovered that these theories violate stochastic dominance. They violate weak separability. They are outside the middle ground. And there was a consensus, and I agree with it, that those theories are not sufficiently interesting for economists. So they are not behavioral usually you don't want to see. That to fix this problem, for instance, for decision under risk, rank-dependent utility was implemented by Quiggin to have probability transformation still, but maintain stochastic dominance, so weak separability. So this is the typical situation for one attribute for behavioral theories. Now let us transfer it to two components being optimized. That's the topic of today. So now in general, I want to do general mathematical, so not only time and risk, but components can be anything and from now on. For instance, maybe one component describe different human beings, maybe the people living in a country. The other component may describe commodities in that country, and the matrix is how you divide the goods in the country and then what is the best way to do it. So here, persons and commodities are the two attributes. Another example is where one one component concerns persons, but the other components concerns uncertainty that can happen. Here we have a matrix where money is given to a man, John, and Lady Mary, but then a coin is tossed heads or tails, and then, for instance, if tails comes up, John get nothing, Mary also get nothing. This is when welfare and risk are combined, and many papers are studying that. It can also be that both attributes concern uncertainty. Imagine that a horse race is taking place, only two horses participating, one of the two will win. It can be ambiguous, no known probability which horse will win. But also a coin will be tossed, heads or tails, and that can have known probability, for instance. So in this situation, if tails comes up and horse one wins, you get €1 and etc. So all these, by the way, such contexts or subsets thereof are typically studied in the Anscombe-Allman framework for ambiguity. So many contexts can be considered. Our theorem applied to all of them. In general, I don't say states and time points, but I say rows and columns when I speak about matrices. And I say matrix, I continue to assume that every cell is a real number, a money amount, let us say, often, or commodity, whatever. And a matrix is a M by N product of cells, and every attribute in this sense is a cell. So it is like this, a square around every cell. However, we can, if we like, also say, well, I would like to say that this is an M-fold combination. I see M rows. I consider this an M-fold combination of rows. I can consider this to be an M-fold product set. So then I say, you know what? There are M rows. I take every attribute as a row. This is an M-fold product set. So then every single attribute is a row. Okay, I can look upon it as a product structure of that kind. It is so. So I can do. Similar story for columns. I can say, I consider this to be an n-fold product set. There are n columns and they are combined. And then every single attribute in this interpretation is a column. I can do that. So all of these things can be done. With that in mind, if I consider it to be a row product set, and then I can define weak separability, that will mean that every single row is separable. Let me go back to this figure. So then I take every single attribute as a row. It's now this blue the lines around it. Then weak separability means every single attribute is now every single row. So then it means that every row in this matrix is separable, every single row. Row monotonicity, that's a term I use for it. The row monotonicity means that thing. Every single row is separable. If I like to say this is an n-fold product set of columns, then every weak separability means every single column is separable. I call that column monotonicity. So that's a bit of terminology that they introduced to prepare. And complete separability is, I can have complete separability, every union of rows is separable, or every union of columns. I can speak about all those things if I like. Well, we want to do behavioral, so also for behavior for 2 or more components. Well, 2 are only today. So in the behavioral approach, typically we would like the weak separabilities to still hold for the 2 components, but the complete separabilities not. You know, that was the middle playground where behavioral theories want to work. Well, now time is coming for a shocking theorem. Theorem: row and column monotonicity imply are equivalent to, now watch out, hold your heart, you know, fasten your seatbelts, so to say. This holds if and only if complete row and column separability hold. Now you may feel a bit confused. Now what is that? Those very weak conditions are equivalent to those very strong conditions? How can it be? Well, it is true, it's correct, it's a very surprising result. But also maybe you can see, oh, wait a minute, what about the middle ground? The middle ground is gone. The weakest and the strongest thing are identical. There is no middle ground. What can behavior still do? So it is indeed a shocking result, so to say. So shocking it is. And things are even worse than what I said so far, because this holds if and only if yet a stronger condition hold, we have complete separability at the level of cells. Not only every union of rows or every union of columns is separable, but every union of cells, also if it's not one of them, like some diagonal, it is also separable. We have even stronger separability than said so far. We have complete total separability, not any interaction of any kind in that whole matrix can be going on. So the weakest condition of all is equivalent to the strongest condition of all, and it feels quite weird and also problematic. What about the middle ground? It can be seen that this holds if and only if preference can be represented by such a functional. They call that additiveness decomposable. This means for every cell we specify an evaluation of that set. Function Vij is the evaluation of Xij, and then the matrix has the value being the sum of those values. This means that every cell has a value on its own, completely unaffected by the others, and also every subset of cells we have complete total separability. Now, this is a shocking result. We should quite discuss it more. What does it mean for behavior? Well, quite dramatic implications. But also the history is something interesting to discuss. But I'm going to discuss the history in the next recording. So that will be a sort after talking about section 2 before we go to section 3.